Thank you. Hello, everyone. My name is Iuna. I'm going to give you the last public talk of this cycle of public talks of the AstroCamp 2022. And my title is Infinities. But before we dive into infinities, I will have to introduce you to a concept of George Cantor, which is the concept of cardinality, cardinal numbers, and cardinal numbers, like cardinals is a shortcut for cardinal numbers. These are a specific kind of numbers as opposed to ordinals, which are a different kind of numbers, which is a completely different universe and gives us really interesting other numbers and infinities, but we don't really have time to go to those, so we'll keep on the cardinals today. The cardinality of a group is basically, simply put, how many elements the group has. So if, for example, you want to know how many bananas are in this set, you just go on and count them. You say 1, 2, 3, 4, and you know the cardinality of this set of bananas is 4. It's 4. 4 is a cardinal because it talks about an amount and not an order. The problem is when we get to infinite groups, we don't know how to count to infinity. So we have a problem. How do we know how many elements an infinite group has? So let's rewind our steps and pretend we don't know how to count to 4. There's another thing. Imagine we have a bunch of toys and someone told us these toys are exactly 4 of them. And we could simply pick up the bananas, pick up the toys and put them side by side, align them and get 1 to each. We get a 1-to-1 correspondence and every banana gets a different toy, every toy gets a different banana. And we know that the number of bananas is exactly the same as the number of toys. The same strategy we can use for infinite sets as well, because it doesn't mean we have to count. So if we have, for example, the set of even numbers and the set of natural numbers, at first it looks like the natural numbers are like double as many as the even ones. But that's basically our finitely thinking brain trying to trick us. Because actually, if you write them down like this, you can find a correspondence. If you do 2 times the natural numbers, you get to the even numbers with a 1-to-1 correspondence. Every even number gets a different natural number and every natural number gets a different even number, which means they actually have the same amount of numbers. That's for cardinality. They have the same cardinality. But then the point is, when you think about infinities, most people tend to think about big numbers, like really big numbers. But you see, 1 million is a big number. This really controversial number that might or might not be 1 billion is a big number. It's even bigger than 1 million. And this one, which is 1 billion for the other ones, is even bigger. You can come up with really big numbers. Look at a Google, which is a 1 followed by 100 zeros. And you can even imagine a 1 followed by a Google of zeros. The point is, no matter how big a number you come up with, you can always find bigger numbers, bigger and bigger numbers. You can simply just add 1 and you've got a bigger number. That means this way, we will never get away from our finite, even though big, but always finite numbers. So with this, what is then infinity? For many people, it's the biggest number possible. Everything. For mathematicians, it mostly is just anything that's bigger than any finite number. That's how mathematicians work. They do it simple. But then there comes a bunch of mathematicians and they come up with a lot of things that are bigger than any finite number, and we're confused again. So let's just try and start simple with the smallest of all infinities. This is the infinity you get when you start with 1 and you count 2, 3, 4, 5, and you go on forever and ever and ever until infinity. This is called countable infinity, as you get there by counting. But countable infinity is not actually a number. Countable infinity is a description you give to numbers which are in this case infinite, some numbers, but it's not a number. On the other hand, Aleph null is a number. It is the number of elements of the set of natural numbers. It is the numbers of hours and forever. It is the number of digits of pi. There are many sets with Aleph null elements, and using the strategy we had before, you can find a few of them. For example, Z, the set of integer numbers, has the same cardinality as the natural numbers, which might not look very easy to get there, because Z does not have a first number. How can I assign a first number to the set? But we should not forget that we can rearrange our set. So if you put, for example, we start with a 0, then we go 1, -1, 2, -2, 3, -3. We can go and put them in a line, align this line with the naturals, and we get a one-to-one correspondence. That means Z has the same cardinality as N. The same goes for Q, the rational numbers, which looks even more counterintuitive because there are an infinite number of rational numbers between 0 and 1 alone. But even this way, you can find a way to get one-to-one correspondence between Q and N. You all know that Q, or the rational numbers, are those numbers which you can write as a quotient between a natural and another natural, or an integer and another integer. So you can write them down in a table like this. You put the numerator in the row, in the columns, you put the denominator in the rows, and this way you can write down every single rational number if you get an infinite table. Now, if you draw a line over this table that gets every single one of these numbers on the line, this line is infinite and can go forever and get every single number, you can take this line, straighten it up, pull the numbers with it, and put the naturals on top of it. Of course, some might be repeated, so you don't need to put it in the line, but it is still a way in which you can get one-to-one correspondence between the naturals and the rationals. Now we get to something different, which is, after this Aleph null, we still have bigger infinities. And for you to understand, to get the feeling of these infinities, I want to use an analogy which is very much used around everywhere, basically, and which is the Hilbert Hotel. I want you to imagine you have a hotel which is infinitely long. It has an infinite amount of rooms. It has a first room, but then it has every possible number after it. I want you also to imagine that this hotel is completely full. In every room, there's a guest. But then suddenly there comes a new guest, and this new guest wants a room. And it's just a normal finite hotel. The manager just tells them, I'm sorry, we have no room for you. You'll have to find another hotel. But not in Hilbert Hotel. In this hotel, the manager goes and asks every single guest to move one room forward. That means person in room 1 goes to room 2, and room 2 goes to room 3. And this way, every single person has a new room because every number has a next number. But room number 1 gets free and the person can move in. This manager still knows what to do if he gets an entire bus full of people. Let's say you get 50 more people. You just ask every single person in every single room to move 50 rooms forward, and you get 50 rooms to get your people in. But what if you get a bus that is so long that it never ends? It's infinite. It has an infinite amount of people in it. The manager can't just go and ask everyone to move an infinite amount of rooms forward, because which room would person from room number 1 go into? There's no room number infinite. No, much less is there an infinite amount of rooms number infinite. So the manager will have to come up with a different strategy. In this case, you can, for example, ask every person to move to the room of double its room number. That means you get to move everyone to exactly the double. And this way, every guest in the hotel gets a new even numbered room, and all the odd numbered rooms get empty. It is always possible because every number has a double, and the person in that double will still move to the next double. So you have free room to go to. And this way you can fit all the infinite people in all the infinite amount of odd numbered hotel rooms. After that, imagine there come more buses and more, an infinite amount of infinite buses. This might be a little trickier. The manager might have to think a little bit about, but he's not that easily defeated. He still gets a way to put them all in his infinite hotel. He pulls out a spreadsheet. He puts in the columns, he puts the room number or the seat number of the person, and the rows he put if they're in the hotel or in which bus they are. And he has this infinite spreadsheet where each square is exactly one guest, either from the hotel or from the buses. Now, if he just went and allocated a number to each square, if he went over to the hotel first and put the numbers like this, he would never reach the end. He would never go to the buses. But if he uses the zigzag we used for the rationals, I don't know if you remember that one, he can find a way to get an infinite line that goes over the entire spreadsheet and get every single square with a different number, which means every single person with a different room. And this way, he still manages to put all these people into this infinite hotel. Now imagine there comes a bus that is so big, it's not only infinite, it's even bigger than the other ones. This bus does not have seat numbers. In this bus, every person has an ID number, or you can call it a name. It is a sequence of zeros and ones, but it's infinite. And every possible sequence is represented in the bus. And then this is the moment when the hotel manager has to say, I am sorry, I have no room for you, because this infinity is bigger than the infinity of the hotel. And then the people from the bus might think, but how is this possible? Your hotel is infinite. How come we don't fit in it? And the manager will tell them, there's no way I can put you all in a list and get every one of you assigned to a different number. And then even if the people on the bus, they come up with a list, with the most difficult algorithm they could find to get everyone on the list, there's a simple way to prove that at least one person is not on the list, which means they cannot put everyone on the list, and there will be people without a room. This method is quite simple. You just take the first digit, the first number, the second of the second, the third of the third, and so on, and you go along the diagonal. You write down this number, and you flip every 0 to a 1, every 1 to a 0. This number is definitely not on the list, because it's different from the first one in the first place, it's different from the second in the second place, it's different from the third in the third place, and it's different from the 57th in the 57th place, and different from any other in at least the diagonal place. That means you do not have this number on the list. There's no room in this hotel for this person. And with this, we get to an infinity, which is bigger than Aleph null. It is called uncountable infinity as opposed to countable infinity. And it basically, told in simple terms, is any amount of things that can by no means be put on a list. For that same reason, some people call it unlistable infinity. An example of this is the continuous interval between 0 and 1. In a very similar way, you can say, okay, we will build a list of it, whichever way, but you get the diagonals and you flip every 0 to a 1, everything else to a 0, and you got a number that will not be on the list the same way as you had before. So the continuous interval between 0 and 1 cannot be put on the list, cannot get a one-to-one correspondence with the natural numbers. That means that the number of elements between 0 and 1 is bigger than Aleph null. These upside strokes mean that we are talking about the cardinality of whatever is in it. Yes. Okay, but how much bigger is it actually? For that, I need to introduce you to another concept of George Cantor's set theory, which is the cardinality of power sets. If you have, for example, a set called A, which has 3 elements, 1, 2, and 3. The subsets of this set are any kind of set which has no element that is not in A. For example, you have the set which has 1 and 2, 1 and 3, the set that has only 1, the set that has 2 and 3, and even the empty set. The power set of A is then the set that contains every subset of A. It is quite simple to understand that you can build this power set by taking one after the other, the subsets you want to put in, and you will ask yourself, will I put the 1 in this subset? If yes, will I put the 2? If yes, will I put the 3? If yes, I got the subset 1, 2, 3. If always no, I get the empty subset, and you can see that this way you will get every single possible subset of A. Also, quite understandably, the number of subsets you get is 2 times 2 times 2, because every time you have to make 2 choices and then 2 more choices and 2 more choices, you get 2 times 2 times 2, which is 2 to the power of 3 equals 8 elements, which is exactly what we had before. You can also imagine that if A had 1 more element, let's say a 4, you would have to ask yourself for each of these subset again, will I put or not the 4 inside, which makes it a 2 times 2 times 2 times 2 set, because you have twice as many options. With this, you can probably follow that any set with n elements, the power set of this same set will have 2 to the power of n elements. And George Cantor even got a different theory, theorem actually, it has been proven, which says that the power set of a set has always more elements than the original set itself, even if we're talking about infinite sets. With this, let's try to get the power set of an infinite set. And this infinite set will be the natural numbers. Let's try and first write them down, because we want to do it step by step. We know for sure by what we have just seen before that we'll have 2 to the power of aleph null elements, and that this should be more than aleph null. Now, to build a power set, as we just saw, we start with subsets. So let's take some subset, for example, the subset with 2 and 3. Let's try and write it down in a different way. We say yes if the number is in the subset, and no if it's not, just like this. Now let's substitute every no by 0 and every yes by a 1, and then we put 0 dot before just for the sake of notation. This way, you can write down every single subset of the natural numbers with this notation in a way that is very obvious which subset we are talking about. It means you can write down, for example, the subset which has only the even numbers, only the odd numbers, the subset that contains only the 1, the subset that contains the entire set of n, the subset which is only the empty set, or any other subset. So the power set of n is every possible number with any possible combination, which is 0 dot, and then any combination of 1s and 0s. Now I want you to note, which you probably know already, is that every real number has a binary representation. For example, 0.75 in binary is 0.11, which is 0.1100000000 to infinity. Even pi has a representation in binary, which is, of course, infinite. I want you to note 2 more things. One is that 0 and 1 in binary are still 0 and 1. That means that the interval between 0 and 1 in binary will be exactly the interval between 0 and 1 in decimal, which is the normal way we usually write. I want also that you notice that 0.11111111111 forever is exactly equal to 1, not approximately, but exactly. Just the same way as 0.9999999 forever in decimal is exactly equal to 1, because it is 3/3. So it's exactly equal to 1. Okay, that means that the power set of n, which is the representation, every possible combination of numbers between 0 and 1, means it is exactly equal to the interval, the continuous interval between 0 and 1. It's just a different form of writing it down, which means it obviously has the same amount of elements. So we saw that the power set of n has 2 to the power of aleph null, so 0, 1 has 2 to the power of aleph null. Yeah. Okay, there are a few more subsets with 2 to the power of aleph null elements. I'll probably just list them to you if you want to know exactly how we get to these. You can ask me later, because I'm not sure if we'll have time for this. We have the set which is the open interval between 0 and 1. We have the entire real line. We have the entire real plane, and even any real n-dimensional space. They all have 2 to the power of aleph null elements. Now I have a little curiosity for you, which is if you go to infinity, not by cardinals, but by ordinals, you get to something that is aleph 1, which is by definition the next biggest infinity after aleph null. And George Cantor built a hypothesis called the Continuum Hypothesis, which says that the real line or the real numbers are exactly aleph 1. Which means he says that the power sets of aleph null get exactly to Aleph1, Aleph2, Aleph3, the way they align. And it also says that there's no cardinality between the naturals and the reals. What is funny about this hypothesis is that it is provably unprovable, which means it has been proven that it cannot be proven wrong, and someone else has proven that it cannot be proven true. Well, that was just a fun fact. Now we go to infinities again. After all this, you got the power set of n, you got the power set of n, and you think to yourself, how many infinities are there? Can I just keep power setting my sets? The answer basically is yes, you can keep power setting. And by the theorem of George Cantor, you see that it always has to be bigger than the one before, so it cannot be equally large. But what if I power set Aleph null times? I mean, that's a big infinity, but you can even go further. You can power set, instead of Aleph null times, you can use this big infinity times to power set, and you get an even bigger infinity. And you keep going like this. Actually, you see the number of infinities, you have noticed by now, has to be infinite. But exactly what kind of infinity amount of infinities are there? Well, it's bigger than Aleph null, definitely. It's bigger than 2 to the power of 2 to the power of Aleph null. Actually, even if I do 2 to the power of 2 to the power of 2 to the power of 2, and I go on like this forever to the power of Aleph null, and even if this forever is a big infinity that goes on forever, and I can do this in big infinity amount of times, and even a really big infinity amount of times, and I can go on like this forever, and I get a really big amount of infinities, a really big infinity amount of infinities. That raises the question, is there an infinity that is bigger than any other infinity? An infinity that is so big that it can contain every other infinity, and that it is the number of infinities that there are, because the number of infinities must definitely be bigger than any infinity, just the same way that the number of finite numbers has always to be bigger than any finite number, because as long as you find a finite number, you have at least as many finite numbers to get with it. The same goes with infinities. If you find, no matter how big an infinity you can find, you can always power set that amount of time. So you can build with whatever infinity, you can build exactly that amount of infinities, and always one more by power setting it, just the same way as before we had always one more by just adding one. So this is the point where we think, but we did manage to get over this first threshold. Why shouldn't we be able to go over this second threshold, which actually is a third one? And this is the point where mathematicians do what mathematicians do. They say, let there be, and there is. Mathematicians defined a number that is bigger than all these infinities. They say, this is, by definition, a number, and so it is. The problem is, these inaccessible cardinals, this is what they call them, are basically more and more and more and more infinities. You can go on, and this stair will basically never end. So some mathematicians end up then trying to get an infinity that is still bigger, that can go over all of them, that can contain them all. They call it the big omega. The problem with this is that it is by itself a contradiction. It cannot exist, this number, because as there cannot exist a box that contains all boxes, for it can never contain itself, this infinity cannot exist as well. And many have tried by building this infinity and creating a lot of axioms around it to find a way to make it exist, but not yet had someone succeeded. And so this infinity cannot exist, and until now, we don't know. But well, that's basically how I want to finish my presentation, by just telling you that the number of infinities is so big that no matter how large an infinity you can come up with, it will never even be able to approach or to get close to describing how many infinities there are. Thank you.